Today, we are diving headfirst into a truly fascinating journey. We're going to completely demystify one of the most famous and, honestly, one of the most misunderstood scientific concepts in human history, the special theory of relativity. Now, I know what you're probably thinking. Relativity? Isn't that just for theoretical physicists staring at chalkboards full of incomprehensible math? Absolutely not. My goal today is to break down special relativity step by step, from the ground up, with zero intimidating equations. We're going to pull back the curtain on the very fabric of our reality. And I promise you, it's going to be a remarkably fun, mind-expanding story. To kick things off, we're going to explore why understanding relativity is actually as natural as understanding the everyday objects around us. Think about riding a bicycle. Why does your bike fall over when it's perfectly stationary, but stays perfectly upright the second you start riding it? We intuitively accept that motion changes the physical behavior of the bike, right? Well, the authors of our source material, Helmuth Gunther and Volker Müller, make the brilliant argument that we can comprehend relativity with that exact same intuition. We really don't need to take the most difficult, math-heavy route to get an intimate knowledge of how the universe works. Now, usually when people teach special relativity, they follow Albert Einstein's original method from 1905, hitting you immediately with his mind-bending claim about the universal constancy of the speed of light. But instead of just throwing you into the deep end right away, we are going to follow a breadcrumb trail of physics through a new set of fundamental logical rules. We're going to build this up logically, step by step. By the time we actually reach Einstein's monumental conclusions, they're going to feel completely inevitable to you. So here's the crucial starting point. To understand the universe, we first need basic tools to measure it. You see, mechanics and the description of motion in space and time simply cannot be separated. If we want to describe an event, we absolutely have to know where it happened and when it happened. To do this, we require perfectly identical standard measuring rods to measure distance and identically ticking normal clocks with a set period to measure time. We just have to guarantee that we have enough of these identical tools distributed everywhere. Simple enough, right? But wait, here is where the story gets incredibly interesting. What happens when these perfectly standard, trusty measuring tools suddenly start moving? It seems like a super simple question. If I take a 1-meter ruler and slide it across the table, is it still exactly 1 meter long? If I take my clock and put it on a fast-moving train, does it take at the exact same rate as the clock I left back at the station? The answer to this introduces the very first major glitch in the matrix of our everyday reality. And this beautifully illustrates what's known as the Fitzgerald-Lorentz contraction. Our sources reveal a truly startling truth here. The physical space an object occupies literally shrinks in the direction it's moving. I'm serious. A moving ruler is genuinely shorter than a resting one. If we have a system at rest, we observe a rod having its full length. But if that exact same rod is set into motion with a velocity, we will measure a new, shorter length. The physical space it takes up literally contracts. Now, you might be wondering, okay, how do we actually know this isn't just some mathematical trick? We know because of hard physical evidence, most notably the famous Michelson experiment. This was a massive historical key for special relativity. Scientists used this brilliant device called a Michelson interferometer. They took a coherent light wave from a source, hit a semi-transparent plate, and split it into 2 coherent waves propagating down 2 different arms. By reflecting them back and observing the interference pattern where they met, they could definitively prove that the moving rod is genuinely shortened. So, if motion can warp space, what does it do to time? That incredible realization forces our minds right to the next logical step. We know that space and time are intimately connected, and we just proved that space warps, that lengths physically shrink when things move. So we absolutely have to ask ourselves, what on earth happens to the very ticking of time itself? What happens to a moving clock? Einstein called this realization his experimentum crucis, the deciding experiment. Moving clocks literally tick slower than stationary ones. A stationary clock has a normal resting ticking period, but a moving clock takes longer to tick. It actually falls behind. And it is vital to understand that the technical construction of the clock doesn't matter at all. Regardless of whether you're using a good old mechanical pocket watch or a highly modern atomic clock based on atomic oscillations, the time dilation effect is exactly the same. Motion literally slows time. Einstein actually proposed this way back in 1905, but it wasn't until 1938 and 1939 that precision experiments definitively proved it in the real world. Scientists looked at hydrogen atoms moving incredibly fast in channel rays. These atoms act like tiny, perfect oscillating clocks, emitting a specific red spectral line. When the atoms were moving at extremely high velocities, the frequency of that light shifted. It was a relativistic correction to the classical Doppler effect, proving beyond a shadow of a doubt that this bizarre time dilation is an absolute physical fact. We really have to pause for a second and just marvel at this beautiful reality. The space-time fabric of our universe operates under deeply non-intuitive rules. We have empirically determined that the physical universe we inhabit is shaped by motion itself. In our universe, motion mathematically shrinks space and slows down time. It isn't some optical illusion, it is the fundamental geometry of our existence.
But this raises a burning question, doesn't it? It just doesn't fit our understanding of symmetrical connections in nature for these things to happen randomly. Why do moving rulers shrink and moving clocks slow down simultaneously? There has to be a unifying law governing this glitch in our everyday perception. There must be a profound reason why nature behaves with such bizarre yet perfectly synchronized symmetry.
And here is the answer. Here is Einstein's ultimate masterstroke. With up to now unparalleled precision, scientists have determined that the speed of light in a vacuum, represented by the letter c, is a universal constant. It is the absolute cosmic speed limit. And the most staggering part? It is completely unaffected by how fast the source of the light is moving or how fast the observer is moving. Whether you are standing perfectly still or flying in a rocket ship at half the speed of light, a light beam will always pass you at the exact same speed, no matter what. Think about what this means for a moment. If the speed of light absolutely cannot change, if it's rigidly locked as a constant in every single inertial frame, then something else has to give. Distance and time cannot be absolute. Because speed is just distance divided by time, space and time must bend, warp, and distort to accommodate the unyielding speed of light. This perfectly and elegantly explains exactly why our rulers shrink and our clocks tick slower. So we've solved the mystery of space and time. We finally understand the mechanics of the stage we live on. But this incredible theoretical framework leaves us with a massive question about the actors on that stage. If space and time are constantly warping to protect the cosmic speed limit, what happens to the energy of motion? What happens to the actual mass of an object as it accelerates closer and closer to that unyielding limit?
This brings us right to the climax of special relativity, E equals mc squared, the profound principle of energy-mass equivalence. Einstein realized that energy and mass are not two separate things. They are the exact same thing in different forms. This means that as you pump energy into an object to make it move faster, the inertia, the mass, of that object actually increases. The energy of motion literally adds to the object's mass, making it harder and harder to accelerate. And that is precisely why no mass can ever reach the speed of light.
Now, it's one thing to do the math and marvel at the theoretical beauty on a chalkboard, but to truly trust it, to know it is the absolute fabric of reality, we have to look to the stars. How do we physically ground these wild, abstract theories in real-world science, especially when considering the massive gravity of planets and stars?
That is where incredible structures like the Einstein Tower Observatory come into play. You see, the rules of special relativity hold true so long as the influence of gravitating masses can be neglected. But in 1915, Einstein showed that massive gravitational fields also alter time and space, moving us from special relativity into general relativity. Observatories were absolutely essential to test if these heavy masses act as sources of gravitational fields that actually modify our relativistic effects.
And the precision tests over the decades have just been staggering. Back in 1925, an astronomer named Adams measured the gravitational redshift in the spectrum of a white dwarf star known as Sirius B. Then, later in 1959, scientists Pound and Rebka brought it closer to home, measuring the frequency shift right here on Earth using highly precise light absorption techniques. These experiments definitively proved that gravity distorts time precisely as Einstein predicted. What you really should take away from all of this is a profound sense of awe. The rules of relativity aren't just for fast-moving hydrogen atoms in a laboratory or for distant collapsing white dwarf stars. They represent the interconnected, fundamental fabric of the reality you exist in right now. The universe is a single, unified stage where space, time, mass, and energy all dance together in perfect, mathematical symmetry. So I want to leave you with this final provocative thought. Take a look at your own watch or the clock on your wall and really think about it. Because of the undeniable laws of relativity, the very mass of the Earth beneath you, the gravity holding you to your chair, is actually altering your own clock right now. Time is ticking slightly differently for you in this exact moment simply because you exist within a gravitational field. The universe is far stranger and far more beautiful than we ever could have imagined. I really hope this explainer has sparked your curiosity to go out and learn even more about the incredible reality we share